Alright, so today we're going to actually be looking at some application problems of using quadratics, specifically in factored form, which is what this chapter is about. So here's our first problem. Okay, we have, say we're launching something. So we could look at a graph like this one here. You might imagine, say, a person standing on a cliff, right, and then throws a message in a bottle out to the ocean. I don't know, for example, right? And that bottle will undergo this parabolic path, which is represented by a quadratic function. And we can represent that by, say, a quadratic function in factored form. Okay? Why would we want to use factored form? Because this would be a zero location, and that's when our message in a bottle will hit the water, or how far it will travel. Okay, so that will tell us how far it travels. Well, we can use factored form to easily find those zeros, and therefore know how far it travels. So that's a good application for factored form. All right. Another example, which is one we're going to look through, is the population of a small town is modeled by this equation. Okay, so we have an equation right here for the population of a town, where P is the population in thousands. So that means if P is 100, then the population is 100,000. And T is the time in years, where if T equals 0, the year is 2000. So that means if T is 10, the year is 2010. If it's 20, the year is, well, currently 2020. All right? And we have a graph of this function right here. All right, so here is, that's our y-axis, which is population. And our x-axis down here is time, years from 2020. So right there, years from 2000, not 2020. Right there is the year 2000. Meaning if we look at this function, right, it crosses this y-axis, which is the year 2000, at 300. So the first question says, what was the population in 2000? Well, that is your y-intercept for our case. And so we saw that is about 300,000 people. Okay. Well, what about 2002? We can try look at our graph here. Okay. Here is 2 for time. If we go up, there's 2002. Now looking over, it's a little bit harder to see. You might be able to estimate. Maybe you'll say maybe 320,000. But if you want to be more exact, what we're going to do is use the equation. So if we use the equation, we can substitute t equals 2, or if p is a function of time, which it is, we use function notation, we can find p at 2. So to do that, we substitute 2 in for t. So we have 0.5 times t squared, or 2 squared, plus 10 times t, or 2, plus 300. So now we're just going to simplify. So 2 squared is 4, multiplied by half is just 2. 10 times 2 is 20, and then we have 300. So that gives us 322. So our estimation was pretty close of 320,000. The actual population, remember that P is measured in thousands. So the actual population would be 322,000 people. All right. Now, so the next question says, determine in which years the population of the town was 450,000. It's a little bit trickier. So here we got t equals 2 because it's the year 2002. Now it's not telling us what t is. It's asking us to find t when p is 450,000. So because p is measured in thousands, we're going to actually say the value of p is 450. That would represent a population of 450,000. Okay? And I'm going to set that 450 equal to our equation. And then we have to solve for t. So that equals 0.5 t squared plus 10t plus 300. So now I have this equation here, right here. And there's going to be two values of t, because this is a second order equation. It's a quadratic. There'll be two values of t. We can figure out when they were. To do that, we're going to have to solve the equation. So let's bring this 450 over to the other side. So we're going to subtract it from both sides. So we're going to end up with 0 on the left. And on the right, we'll have 0.5 t squared plus 10t. And then we get 300 minus that 450. So 300 minus 450 is negative 150. So this here is a quadratic equation. And we're going to have to solve it. There's a couple ways that you can solve it. You can use the quadratic formula. Some of you might remember that from grade 10. But we're actually not going to go into the quadratic formula until chapter 4. So what we're going to do is we are going to factor this. So you have a couple ways of factoring. You could use like the x method, okay? And because you have 0.5, but we can actually fix this in a sense so that it becomes more of a simple trinomial. To do that, we can multiply every single term by 2 on both the left and the right side. Now 2 times 0 still gives us 0. This is why this is a great trick. And 2 times a half just gives us 1. Then we're left with 2 times 10, which is 20. And 2 times minus 150, which is minus 300. So now it's a simple trinomial. Before, you didn't have to do this. You could have used either decomposition or that guess and check x method if you prefer. You didn't have to do this little trick. But it certainly does make it easier, because now you just need to think, okay, what are two numbers that multiply to give you negative 300 and add to give you 20? I'm going to pause there and let you think. All right, so we have negative 10 and positive 30. Multiply to give you minus 300 and add to give you minus 20. Now, we need to find what those zeros are. So basically, what value of t would make this bracket 0 and what value of t would make this bracket 0. For this one, t could be 10. So if t is 10, 10 minus 10 is 0, and 0 multiplied by whatever this is going to equal 0. That satisfies the equation. Over here, you'll have t equals minus 30. Okay, so if you look at our graph, and if we went forward to 10, which is right there, you can see it does cross at what looks to be 450,000, so it works. Now, notice that this is a parabola. Because it's a parabola, it's going to start coming back up at one point. So you may assume, well, according to the equation, if you go back 30 years to the year 1970, the population was 450,000 as well. Well, that may not be true, right? Our function may only predict a recent time scale and sort of extrapolates to the near future. So we might only be interested in the population in 2010. But of course, for us, that was 10 years ago. Right? But of course, when this problem was made, it was 10 years in the future. Okay. So looking at the next page, I want to look at, all right, what is the actual difference between a quadratic equation and a quadratic function? Now, we talk about zeros and roots a lot. So let's look at an example. Here we have a graph. This is definitely a quadratic. It looks like a quadratic. Let me just zoom in a bit here. Now, if we wanted to figure out an equation, well, according to factored form, we just need to figure out where it crosses the x-axis, which is here and here. It's hard to see. Let me zoom in a bit more. So this is at -1, and this is at +2. Therefore, our equation would look like x plus 1 and x minus 2. Okay, and I'm going to leave it as positive out in front because it clearly opens up. Okay, so that's our x-intercepts. Now, a quadratic equation is where we set this equal to 0. So we're going to set y equal to 0, looking for where those x-intercepts actually occur. Plus 1 minus 2. Now, the roots of that equation are where the values of x actually satisfy the equation, which again is -1 and +2. So there's definitely some common things going on here. And if you have, say, a function to describe a parabola, the x-intercepts of that function refer to the roots that solve the quadratic equation. It all seems like the same thing. We're just making up a whole bunch of different terminology to be a little bit picky, but they do have meaning. So let me just pause there to see if anyone's confused. All right, so let me say that again. So the zeros of a quadratic function, so this is our function. It's a function because it exists over many values. Those zeros of the function, meaning where it crosses the x-axis, are the roots of our quadratic equation, or the solutions which make our quadratic equation valid or true. All right, so let's go over a couple more examples, but this time, of course, I'm going to give you different information, and you're going to have to still fill out this entire row. So this one says the equation is x plus 2 and x minus 1. So the roots, okay, are where this equation is satisfied for what values of x. So in this case, all we really need to do is take the opposite sign. We have x plus 2. So what plus 2 gives you 0? So that's oh, there goes my pencil. So that would be minus 2. Also, what minus 1 gives you 0? Well, it would be positive 1. Okay, and we can write this as our function as well. So we have x plus 2 and x minus 1. And then we can label the x-intercepts, all the same things, right? Zeros, roots, x-intercepts. So we have minus 2, which is here, and plus 1, which is here. Okay, and then we know it opens up. Okay, we could be more specific and we can find where the vertex is given this information, but we did that in a previous lesson, so I'm not going to emphasize it too much. So we open up like that. You could use different colors. All right, let me do one more. This one I'm going to let you try later. Let's look at this one. So this one is saying the actual coordinates, right, for those x-intercepts or zeros. I mean, in the previous one, we can write the coordinates here. Like this would be the x-coordinate minus 2 and 0. And this would be the x-coordinate 1 and 0. Right? Your y value will always be 0 where it crosses the x-axis. So, if this is where it crosses the x-axis, those are our roots, minus 3 and 5. And then we can throw the opposite signs into the equation. This plus 3 and minus 5 And we can write that as our function. I'd prefer it if this was actually function notation, but whatever. X plus 3 and x minus 5. And we can write our roots as our x-intercepts. So here's minus 3 and plus 5. And again, all these examples have a positive 1 value for a. So it's going to open up like this. Okay, so I'm going to stop there and let you try, give you some time to try the other two.